Hi there. Welcome to Lecture 9 of Machine Learning from Data. We're going to continue our study of linear models with logistic regression, and we'll also introduce a general purpose algorithm called gradient descent, which is useful for minimizing functions, in particular ensemble error functions. Okay, quick recap from last time. Okay, we talked about the linear signal W transpose X and how it can be used to solve different kinds of problems. Classification, regression, logistic regression, which is the focus of today. Okay. Now, this lecture followed an entire theory on how we maintain this link from E in to E out. Okay? And basically, you need to learn with a hypothesis set that as small a VC dimension as you can get away with. Okay? And linear models are ideal for that. The linear perceptron VC dimension is just D plus 1. Okay? So now that you've got this, simple hypothesis set, how do you get the ensemble error small? And that's where the important takeaway from last time is, you have to construct good features that are relevant for the task that we're trying to solve, relevant for the problem that we're trying to solve. And we introduced the digits data, which we will be working with throughout the semester. Here are examples of 5s, here are examples of 1s, and we introduced features which are intensity and symmetry. Now we got those features without looking at the data, just thinking about the problem and what distinguishes a 1 from a 5. Okay, and this is just 2 features. So if you use a linear model with just 2 features, its VC dimension is just 3, and bam, you've got E in close to E out. And look, if you've chosen good features, you can get E in small. Okay. Now, on the practical side, we introduced the pocket algorithm, which is, now that you've gotten good features, you still need to go and find the hypothesis that gets the smallest ensemble error. Okay? And the PLA, when your data is not separable, goes on forever. The pocket algorithm can tolerate errors. It's simple, it's efficient. Okay? And then we talked about linear regression, where the task is to predict credit level, a real number. Okay? And the error that we use to measure how good are your predictions is the squared error. And we showed, or we derived the pseudo-inverse algorithm, this beautiful algorithm that, efficiently in one step, without using an iterative process like the pocket algorithm. So in one step, the pseudo-inverse linear regression algorithm finds you the weights that minimize the ensemble squared error. Okay? And so, one of the applications of that is to approach a classification problem as if it were a linear regression problem. Use the pseudo-inverse algorithm to get a set of weights, okay? And then use those weights as the initial weights in the pocket algorithm. Okay? So linear regression is in and of itself an important problem when you're trying to, for example, predict a credit level. Okay? And it can also be used as a startup phase for the pocket algorithm. Okay, today, logistic regression. And, let me give you this example where, someone's about to have a heart attack and we'd like to know what are the chances they have a heart attack over the next year. Okay, so here's a input. This person is 62 years old, is male, 120 milligrams, blood sugar, HDL, LDL, mass, height, You can think of this as the biological profile of your, your applicant in some sense, of your input. Okay. And now if we were doing classification, you should say yes or no, this person will have a heart attack in the next year. Okay. Now, in the logistic regression problem, don't tell me yes or no, will they have a heart attack? Tell me the likelihood of a heart attack. And if the likelihood is, let's say, 0.9, this person is in a serious situation. If the likelihood is 0.1, the person is not in a serious situation. So the output of the logistic regression is not a binary plus or minus 1, yes or no answer. It's a probability that's between 0 and 1. Okay, so how do we do this? With the linear signal, we take the linear signal, which is W transpose X, and we pass it through a function, a sigmoid, what we can call a logistic function, okay, which takes the input W transpose X, takes the signal and transforms it smoothly into a real number from 0 to 1. Okay, so when W transpose X is very small, close to negative infinity, okay, you're going to output 0, and when W transpose X gets very large, you're going to output 1, and then it's going to smoothly interpolate. Okay, so let's move to the board to discuss logistic regression. We'll derive the error function, we'll derive the algorithm, and that's where we'll see that we need gradient descent. Okay, so logistic regression. And the task is to predict a probability. So here y is in 0, 1. Okay, and so the idea is you take the linear signal S equals W transpose X. So you take the linear signal, and apply a transform to it, goes to theta of W transpose X. And so our final H of X is equal to theta of W transpose X. And let's see what this function theta should look like. Okay, so on this axis, I will plot W transpose X, 0. Think of this as going to plus infinity, going to minus infinity. And, here I'm going to plot, so this is the signal. Okay, and I want it to go to +1, here. And I want it to go to 0 here. So this is 0, this is 1. Okay. Okay, and when the signal is very large, I'm at 1. And when the signal is very, very small, negative, I'm at 0. And I want to smoothly interpolate between those two. This is called a sigmoid. Okay, and you might think that, when the signal is 0, maybe it should be a half. That seems like a reasonable choice. So there are many choices of functions that we can pick that have this sigmoidal behavior. Okay? And so, this gives us a little bit of flexibility to choose a sigmoid that's mathematically convenient. There's no real reason to prefer one over another. And so the sigmoid that we're going to choose is a particularly convenient sigmoid. So theta of S has this mathematical form, e to the s divided by 1 plus e to the s. And you can easily verify that at the two limit, when s goes to infinity, you get e to the s over e to the s, which is 1. And when s goes to minus infinity, you get 0 over 1 plus 0, which is 0. Okay. Now, this turns out to have some nice mathematical properties. Let me just summarize them. Okay, so the first is that we can observe that this is equal to 1 over 1 plus e to the minus s. Okay, dividing top and bottom by e to the s. And so this means that 1 over theta of s is equal to 1 plus e to the minus s. So a particularly simple, convenient form for the reciprocal. Another useful property of this function is that theta of minus s is equal to e to the minus s over 1 plus e to the minus s. So I plugged in minus s here, which is equal to, if I multiply top and bottom by e to the s, is equal to 1 over 1 plus e to the s. And you see that if I add theta of s, so this guy, and theta of minus s, so this guy, I get 1. So this means that theta of minus s is exactly 1 minus theta of s. Okay. So, we get to choose the sigmoid to use because, we're building our hypothesis set, and all we really need is a reasonable sigmoid, and so we might as well choose a sigmoid that's convenient, and this is a particularly convenient choice for the sigmoid. And we'll see why as we, continue our analysis, why this is a particularly convenient sigmoid. Okay, so this just accomplishes the goal of getting the linear signal and outputting a number between 0 and 1. Okay. Now we need to do a couple of things. The first is we need to address the logistic regression problem. Okay, so how is it presented to us? And then the second is, just because I have a number between 0 and 1 doesn't mean it's a probability. So we need to address how we're going to get a probability. Okay. So, question 1. What's the setup of the logistic regression problem? So setup of logistic regression. And question 2, just any number between 0 and 1 is not going to be a probability. So how do we get a probability? How do we get a probability? Now, let's set up the regression, the logistic regression, and let's think back at that heart attack prediction. Okay, so, and let's think about how we would collect data. So how do we collect data? So we get a whole bunch of patients. Okay, and remember, a patient is represented by the weight, by the weight, the blood pressure, this, that. So the patient is represented, so you have a bunch of patients, just like applicants, they are input vectors, x1, x2, x3, up to xn. And we're collecting data. Okay. And now we're trying to learn a probability. So we're in this supervised learning context, and we would like you to tell us, for this patient, what's the probability they will have a heart attack? For this patient, tell us what's the probability they would have a heart attack. That would be the ideal data for logistic regression, because we're trying to learn to predict a probability. But I have news for you. We don't know how to measure probabilities. Okay. All we can do is take each of these patients, which are an input vector, and see what happened to them a year later. Okay. Did they or did they not have a heart attack? So, all we can observe, we observe y1, y2, y3 up to yn, and yi are, in the set -1 plus 1. That's interesting. Okay, we would like you to tell us data of the form, feature x and probability p of x, okay, for that feature. But we can't measure probabilities. We can only measure whether or not an event happened. Okay? So, where -1 is no heart attack, +1 is heart attack. Okay, and so what we observe here is that the data is exactly the same as if it were a classification problem. So the data is as though we are doing classification. It's as if we've collected a data set that would be the same data set that we would collect if the task was classification to predict ±1. But this is the challenge of logistic regression. We're not interested in predicting ±1 as we would have been with classification. If that's all we cared about, we just run the PLA or the pocket and we're done. We're not interested in predicting ±1. The challenge is we have to predict a probability from the same type of data, okay, that we would use if we were trying to predict a classification, heart attack or not. So it's the same type of data as classification, but we want to predict probability. And that's the challenge. So somehow, okay, from ±1, did the event happen or not, we have to tease out the probability. Okay, we have to somehow infer the probability and learn how to predict a probability, okay, even though all we can observe historically when we're collecting the data set for machine learning is whether or not the patient had a heart attack. That's the challenge of logistic regression. So it's important to understand this challenge, okay, is that, you don't get to observe probabilities, you get to observe whether or not events happen. Okay, so let's see how we're going to do that. Okay. Now, even though we observe, yi is ±1, actually, underlying this observation of yi is ±1, we're imagining there exists a true ground truth target function. So there exists a ground truth target function f. Okay? And in this case, so f of x, and in this case we're in the probabilistic target function world, the non-deterministic target function world. So f of x is basically telling us what's the probability that you will observe +1. Okay? So the probability that you will observe +1 given x is f of x. So this is the case that the observable y is non-deterministic, but there is an underlying target function that we're trying to learn, which is this probability. Okay, and if there isn't such an underlying target function, if there's no pattern, then we're not in business anymore. Okay? And so let's see, what would be the probability of observing -1 given x? Okay, so this would be 1 minus f of x. Okay, because f of x is the probability to observe +1, 1 minus f of x is the probability to observe -1. So even though the data is ±1, we're not trying to predict ±1, we are actually trying to learn f. This is the true probability. True probability. Okay, this is the true probability. Okay. And our goal, our hope, is that the h of x that we learn, so the hope / goal, is that h of x, which is theta of w transpose x, where theta is this sigmoid that we chose, okay, so h of x is approximately equal to f of x. And then we have succeeded. We have constructed a function h of x, okay, by appropriately choosing the weights w, that approximates the true probability function f of x. Okay. Now, let's go back to, classification. Let's go back to regression. How did we go about picking the weights w that accomplished whatever the goal was? The way we went about picking the weights w that accomplished whatever our goal was to identify what's the in-sample error. In the case of classification, it was the fraction of mistakes you were making on the data. In the case of regression, it was the mean squared error, the average of squared errors, okay, where we were trying to predict a credit level. Okay, so and then what did we do? Then what we do is we say, oh, okay, so now that we've identified what makes a hypothesis look good, okay, i.e., minimize whatever that error is, then find the weights that minimize the error. Okay. Now, so our first task, if we're going to pick a final hypothesis G of this form, is we have to pick the weights for that final hypothesis. So we need to pick a final hypothesis G of x of this form, i.e. the weights need to be picked. Okay, and how do we pick those weights? Well, we need to identify what's the right in-sample error and then pick the weights that minimize the in-sample error. So need to identify E in of W and pick weights to minimize E in of W. Now, in the case of classification, E in of W was the fraction of mistakes you made on the data. Okay. In the case of regression, it was the average squared error. Okay, so what is the right E in here? So let me just walk you through that process. And in general, this is a good process to get a handle on. Okay. So, remember, h of x is supposed to approximate f of x. Okay. So that means that, the probability of +1 given x is supposed to be approximately h of x, and the probability of -1 given x is supposed to be approximately equal to 1 minus h of x. Okay, because h is supposed to approximate f of x. So, what this means is, now, if you observe a data point xn for which yn is +1, it seems more likely that, the probability of getting +1 is higher than the probability of getting -1. And so, this is going to be the likely outcome if h of xn is approximately equal to 1. And if you observe a data point, so remember, we only get to observe yn, which is plus or minus 1. If you observe a data point xn with yn is equal to -1, well, that's going to be the likely outcome if h of xn is approximately equal to 0. So, when yn is +1, h should be 1. When yn is -1, h should be 0. And we can summarize that by saying that h of xn should be approximately equal to 1/2 times 1 plus yn. Why? Because look, when yn is equal to +1, okay, then you have 1 plus 1 over 2, that's 1. Okay, and when yn equals -1, you get 1 plus -1, which is 0, so h would be 0. So h of x, or on the data, h of xn should approximate 1/2 1 plus yn. Okay. And so now we can easily construct an in-sample error. Look, E in of w, okay, or let's for the moment call it E in of h, but we know that, to specify h, you just have to pick a set of weights. W E in of h is equal to 1 over n, the sum from let's say from little n equals 1 to big N of h of xn minus 1/2 1 plus yn squared. Okay, so this is the remember, in regression, you try to get h of xn to be approximately equal to yn. Okay. Well, here we don't want h of xn to be approximately equal to yn. We're constructing the squared error so that h of xn is approximately equal to 1/2 1 plus yn. And that's a perfectly fine error to minimize. What it'll do is it'll ask h to be approximately 1 when you observe positive data points, and h to be approximately 0 when you observe negative data points. Okay, and this is, in some sense, you could think of that as the squared logistic regression error. The squared logistic regression error. Okay, and I just did that to show you the process by which we can derive an ensemble error to accomplish the task that we're trying to solve. But unfortunately, no, this is not good. Not good. Okay, and let me give you two reasons why it's not good. The first is just purely mathematical. It is an extremely inconvenient error. Because remember, why did we define this ensemble error? Was because that's the error that is going to grade hypotheses, grade different weight vectors. And okay, so now you've graded the different weight vectors. I need to go and pick the weight vector that got the best grade, that minimized this ensemble error. That's going to be very hard to do. Okay, and okay, so one, it's not mathematically convenient. Two, where's the probability? All we did was we tried to make h of x and approximately 0 or 1 when, depending on the value of yn, but where's the interpretation of h of x as a probability? So it doesn't fundamentally use the fact that h of x is a probability. It does not use the fact that h of x is a probability. And so when we're done minimizing this, there's no sort of expectation that the h of x that we learn will correspond to actually a probability. It'll just be some function, okay, that equates to approximately 1 for all the data points that you saw that were +1 and approximately 0 for the data points that were -1. But where have we said anything about the probabilistic nature of h? Okay. So, I'll keep that on the board. And I'll tell you, what's the better error function? You might say, well, okay, so we derived this, it made sense, but then now you're telling us it's bad. So then what's the better error function? Okay, and I'm going to tell you. So what's the better En? Okay, and what we're going to derive is what's called the cross-entropy error. Okay, and it's going to actually solve both of these problems. Okay, it's going to be mathematically much more convenient, and the derivation is going to intimately use the probabilistic nature of h of x. Okay. And in order to derive this cross-entropy error, okay, I'm even going to introduce you to a new sort of concept called the likelihood. Okay, so the first thing we have to remember is, we have our data set. Let me tell you what the cross-entropy error is. So the cross-entropy error, so at least you know where we're going. Okay, so E in of W is 1 over n of the sum from n equals 1 to big N of the log of 1 plus e to the minus yn times W transpose xn. That is the cross-entropy error. I'll put it in a box. Okay, and we're going to derive that guy. But you might first ask yourself, why? That looks so ugly and complicated, Look, it's got logarithms, exponentials, and so on and so forth. This is a much simpler looking, cleaner error function. Okay, and yes, it might look ugly and more complicated, and it has logarithms and exponentials, but we don't care about how things look. Okay, we don't care about how things look. It's how they behave. And in particular how they behave when we want to now find the weights that minimize the error function. And also, comes with a probabilistic interpretation. So it's ugly, but that's the guy we want. Okay, ugly but behaves well. Okay, so let me go back to the data. We're going to derive this error function. It's going to be mathematically convenient, and it's going to have a probabilistic interpretation. So it's going to solve both of these problems, and in order to derive this, we're going to have to go back to the data. So the data. And I want to remind you, so the data is x1, y1, x2, y2, xn, yn. Okay, good. And remember x, n, y, big N. And remember y, little n. So I'm going to use little n to index and big N for the number of data points. So y, little n is in -1 or +1. But all those details are not what I'm trying to focus on at the moment. I want to focus on the fact that, these data points are IID. So the data is IID. Okay, and so independent, identically distributed. And you might say, why? How do we know that? Okay, so I'm going to pause the video. And, or you can pause the video and think to yourself, why is the data independent, identically distributed? Are we guaranteed that? So we pause the video. And if you're coming back and you said, well, that was one of the foundations, one of the pillars of the theory that we needed in order to establish that learning is feasible. To get this link from E in to E out, we needed the fact that the data is IID, independent, identically distributed. And when you go to your client and your client says, okay, I've got a data set, you first ask them, did you generate these data points IID? Okay, so we're implicitly assuming that we're in the setting where, it's a good thing to minimize the ensemble error, whatever it is. And it's a good thing to minimize the ensemble error only when you've got the link from E into E out. Okay, and to have that link from E into E out, one of the conditions is your data must be IID. Don't ever forget that. Fundamental. Okay, so we can assume the data is IID. Okay, and so we can ask, what is the probability that you observe the values y1, y2 up to yn, given that, the data point inputs are x1 up to xn. So what x1 up to xn? So what is the probability of y1, y2 up to yn, given that they're occurring on the inputs x1, x2 up to xn? Okay, now you might ask, well, why are we doing this? Okay, so you'll see shortly. So this quantity here is called the likelihood. Okay, it's the probability. Think of it as the probability of obtaining the data. Think of it as the probability of obtaining the data. So you've generated the x values, and we're asking what is the probability that you observe the specific y values that you observe. Now, why are we focusing on the specific y values? Because, what we're trying to learn is a way to predict the y values. We're trying to learn the probability of the y values given the x values. That's what h of x is. That's what f of x is. Okay. And if our h of x is approximately equal to f of x, then, this probability, is equal to the probability of y1 given x1 times the probability of y2 given x2 times the probability of yn given xn. Okay, and you might say, well, why is that? IID. The data are independent. And we will write this as the product from little n equals 1 to big N of the probability of y little n given x little n. Okay. So that's the probability of observing the data. And that's exactly where the H comes in. Okay. So the hypothesis that we're ultimately going to produce, has to be, if it's close to F, is exactly capturing this guy. So this guy, is supposed to be H of xn, if yn equals +1, and 1 minus H of xn, if yn equals -1. Okay? Because that's what H is. It is the probability of observing y given x. Okay? And here we are intimately using the probabilistic interpretation of H. The fact that H is outputting a probability. So there, we're fundamentally using the fact that H is outputting a probability. Okay, now it's going to be convenient to have a more compact way of saying this. Okay, so let's now specialize to our choice of H. So H of xn is equal to theta of W transpose xn. Okay, and 1 minus H of xn is equal to 1 minus theta of W transpose xn. Now, if you remember, I told you that the choice of the sigmoid that we made is going to be very mathematically convenient, and here we're going to reap some of that payday because, one of the properties of the sigmoid that we, chose, and you can look back in your notes, one of the properties of this sigmoid is that this is equal to theta of minus W transpose xn. Okay. And this is because theta of minus s equals 1 minus theta of s. So there, we're already benefiting from our particular choice of sigmoid. Okay, so if yn equals plus 1, this is supposed to equal theta of W transpose xn, and if yn equals minus 1, this is supposed to equal theta of theta of minus W transpose xn. But look, when yn is plus, this is plus inside here. When yn is minus, this is minus inside here. So we can summarize both of these equations as theta of yn W transpose xn. Okay? So when yn is plus, this is plus, and we get that. When yn is minus, this is minus, and we get that. So it's a very convenient form. So there's nothing mathematical here. It's just a convenient way of summarizing this fact. It's just a convenient way of summarizing this fact. Okay? And it has to do with the choice of sigmoid. If you are perfectly welcome to choose a different sigmoid if you want, but then this nice convenient, representation of this fact won't be possible. And so the derivation will still be valid, but the algebra won't be as compact. Okay? So this means that we can replace the probability of yn given xn by theta of yn dotted in theta of yn times W transpose xn. Okay. So this guy here is exactly theta of yn W transpose xn. Okay. It's just a mathematical fact due to the choice of our sigmoid theta. Okay. So let's erase that justification. Okay, so the probability of observing the yns for these particular xn's that were generated is the product of the probabilities, which is equal to the product of theta evaluated at yn W transpose xn. Okie dokie. So this is called the likelihood. Derive the likelihood. Well, what use is the likelihood? Okay. Now, let me go back and tell you again, what was the likelihood? It was the probability of observing the y values given the x values. And if your, hypothesis H were f, so if it approximates f, then the probability of obtaining the data should be high. And if it were not close to f, then it's not going to have a high probability for you to observe the data. Okay? So the natural thing to do is to find the choice of weights W that maximizes the probability of observing the data. So choose the weights W to maximize the probability, the chances to observe the data. Okay. Now, this is called the method of maximum likelihood. So this is called the method of maximum likelihood. And the philosophical debate on whether or not this is the right thing to do, well, it's ongoing. Okay? And there are ways we can justify it, there are ways we can poke holes at this. Okay? And
That's not our business. We're going to leave that to the philosophers of mathematics, the philosophers of probability theory, and let them have it out with each other as to whether or not, oh, this is a good thing. The bottom line is, it intuitively makes sense to maximize the likelihood, because a good hypothesis should produce data with high probability, okay? Because the probability should be large when the y's are +1, and the probability should be large. So the probability of observing the y values should be large, no matter whether the y's are +1 or -1. Okay, so a good hypothesis definitely should, a good hypothesis definitely should have a high probability, and so whether we should maximize the probability or should we do something else, well, okay, that's up to the mathematicians. But it's a very popular approach, okay, the method of maximum likelihood. And so we're going to borrow this approach from the math side, from the probability side, and just use it. Okay, so the prescription is to choose the weights W that maximize the probability to observe the data. Okay, so how do we do that? So let me call this thing the likelihood, okay, L. And the prescription is to pick the weights W to maximize L, the likelihood. How do we do that? Well, it looks complicated. You have to find the weights W that maximizes this complex product. Okay, but now I'm going to show you a sequence of mathematical facts, and now here there's no, assumption, or there's no, is this the right thing to do? It's just these are mathematical facts. Mathematical facts. Okay, so if you have any function, let me call it R for argument's sake. Let me call it L of W. Just like here, we have a function L of W. Well, it also depends on the data x and y, but that's fixed. So materially, as far as we're concerned, it depends on the weights W. So you have a function L of W, and you want to maximize with respect to W. Okay, that's equivalent to maximizing the logarithm. Maximize. So you want to find the W which is which maximizes this. So actually technically I should say you want argmax with respect to W of L of W. So you want the W that maximizes this. That's equivalent to finding the argmax with respect to W of log L of W. That's just a mathematical fact, and that's because the logarithm is an increasing function, and you can do this as long as this function L is positive. And it is the case that our function L is positive because our theta is a positive value. So it's a product of numbers between 0 and 1, and that product can be small, but it's positive. So we can take the logarithm of this and find the argmax, maximize with respect to W. But okay, it's also a mathematical fact that if you're maximizing any function, you can maximize any constant times the function. Okay, so this is the same as finding the argmax with respect to W of 1 over n times the log of this function. Okay, now a twist. Okay, finding the maximum of some function, okay, or the argument of the function that attains that maximum is equivalent to finding the minimum of that function. Actually, the argument of that function that attains the minimum if you look at the negative of the function. So this is equivalent to the arg min over W of minus 1 over n log of L of W. Okay. So these are just mathematical facts. Okay. Can't argue with them. If I want to maximize a function, I can maximize its log and find the argument that maximizes the log. I can maximize any constant times the function, or I can minimize the negative of the function. And you might ask, why am I doing this? Well, most of the stuff I'm doing is just cosmetic, but the main thing here was introducing the log. And can anyone tell me why I introduced the log? Pause for 1 second. We'll come back. I introduced the log because the log is this beautiful function that can convert a product into a sum. Okay. So the prescription, which is to choose the weights W that maximize the likelihood, has now translated into the prescription choose the weights W to minimize minus 1 over n times the log of L. And I want to emphasize that that prescription and this prescription are the same prescription. Okay. They will produce the same weights W. And why are we doing this? Because that makes intuitive sense. It's the method of maximum likelihood that's popular in statistical inference. It's not our business to philosophize on whether it's proper. We're just going to borrow the fact that maximizing likelihood is a good thing to do. Okay, and this is the likelihood. So let's see where it takes us. Okay, so we want to minimize what? We want to minimize this guy. So we want to minimize minus 1 over n, the logarithm of the likelihood. But I already told you why we introduced the logarithm, because the logarithm of this product becomes a sum of logarithms. So we want to minimize minus 1 over n, the sum from little n equals 1 to big N of the log of theta of yn w transpose xn. Now we can take this minus sign inside the log, inside the sum, and then you have minus log of something is the same as log of 1 over something. So this is equal to 1 over n, the sum from n equals 1 to big N, minus log of theta, which is log of 1 over theta, yn w transpose xn. But 1 over theta, the other nice mathematical property of theta that I mentioned before, anyone remember what it was? 1 over theta is 1 plus e to the minus theta. So this is 1 over n, the sum from little n equals 1 to big N of the log of 1 over theta, which is 1 plus e to the minus yn w transpose xn. There. That's exactly the ensemble error that I claimed we were going to derive. We have derived the cross-entropy error. Wonderful. Wunderbar. Okay. So, what was the prescription? Okay. The prescription was the learning process. Okay, you can think of this as the training process. So how do you pick your final hypothesis G? Choose the weights W that minimize this ensemble error. Okay. Choose the weights W that minimize this ensemble error. And we just derived it. So choose weights W to minimize this ensemble error. And that's a good thing to do. It intimately uses the probabilistic nature of H in deriving it, and it'll also be mathematically very convenient. Okay. So, how are we going to do that? So let's ask 3 questions. Or 2 questions. Okay, so let's ask 2 questions. Question 1. Does this cross-entropy complicated looking error make sense? Does this En of W make sense? 2. Okay. Well, the prescription was to find the weights W that minimize this En of W. So how to do that? How to find, weights W that minimize En of W. Okay, so we'll address both of these questions, and in doing this, we will introduce gradient descent, and at the end, I'll introduce even another sort of snazzed up version of gradient descent that works very well in practice called stochastic gradient descent. Okay, now, does this ensemble error make sense? So let's see. Supposing Yn is, so remember, we're going to minimize this ensemble error, and ideally we'd like to minimize each term. So let's look at one term where Yn is plus 1. So then this is e to the minus of W transpose Xn. So we're encouraging W transpose Xn to go off. If Yn is plus 1, there's a minus here. So e to the minus something large is close to 0. And that's when this term is minimized. Okay. So we're encouraging, so Yn equals plus 1 encourages W transpose xn to be much, much greater than 0. Okay? And if W transpose xn is much, much greater than 0, then the sigmoid on that is approximately 1. So for plus 1, this guy is encouraged to produce a probability close to 1. When yn is minus 1, so here now this minus times minus 1 becomes a plus, and so for this term to be minimized, you would like to send W transpose xn very, very small. It encourages W transpose xn to be much, much less than 0, and in that case, when you take the sigmoid of that, you output 0. Okay? So this error function does encourage the same behavior that we saw when we derived the bad error function. Okay, and so there are many ways to develop an error function that has that behavior, that when yn is plus 1, h of xn is close to plus 1, and when yn is minus 1, h of xn is close to 0. Okay, there are many ways to derive an error function that encourages that behavior. The way we chose has the nice probabilistic interpretation of h. It maximizes the likelihood, which is a probabilistic error function, and as we're going to see, when we come to address the second question, it'll be mathematically convenient. Okay. So how to find the weights W that minimize the in-sample error? Let's see how we did it with classification. So classification, what did we do? Okay, it was an iterative algorithm, pocket algorithm, pocket/PLA. So at every iteration, we try to improve the weights, thereby improving, minimizing in a little bit at each iteration. At the end, we hopefully have a good set of weights with a very low in-sample error. Okay, or regression. Okay, you could think of the regression algorithm as analytic. So we'll call it the analytic pseudo-inverse algorithm. Okay, which analytically sets the gradient of En of W to 0. Okay, now in our case we have this complicated in-sample error. So for logistic regression, okay, we could take this approach. This is a nice differentiable error function. Why couldn't we take the approach with classification? Because the in-sample error having h in it, and h being the sign of something, was non-differentiable, was not even continuous. Okay? So this error function is nice and differentiable, and so we could, in theory, set the gradient to 0 and find the weights which achieve that condition. But it's not possible to do it analytically. So cannot analytically set the gradient of En to 0. Okay. So we're going to use a hybrid of these two techniques. Okay. While we will want to set the gradient of En equal to 0, similar to regression, we can't do it analytically, so we'll do it iteratively. So iteratively set the gradient of En equal to 0. Okay, that's our approach. Okay, now I'll give you the high-level philosophy of the approach. And when we were kids, we've all experienced this. So you're on this very hilly landscape. Okay, so you're this very, very hilly landscape. Okay, I mean, I don't know what kids play in hilly landscapes like this, but just imagine you're playing around in this hilly landscape with a ball. Okay, so if you randomly throw your ball, okay, depending on where it lands, so the ball could land here, 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 and you'll see why I'm picking these special positions. Okay, so it could land anywhere, so you randomly throw your ball if, let's imagine that it continues like that. And then what happens to this ball? Well, it rolls under the influence of gravity. Okay? And, in these cases it rolls that way, okay, and comes to a stop here. In these cases it rolls that way. Oh, what's this ball? It rolls that way and comes to a stop here. In these cases it rolls that way and comes to a stop here, and so on. Okay, and we're all familiar with this phenomenon. Okay. And, think of this now when you were playing around in real life, this error surface is the height of the hill, okay, the height of the various hills, and, you had an x and a y, dimension that you could move around in. So you have an x and a y dimension. Okay, well, the equivalent of x and y in our scenario are the weights. So you can choose W0, W1, W2, and so on. And for each position in your weight space, okay, there's an in-sample error. So this, slopey, hilly terrain corresponds exactly to E in of W. Okay, and now with the experience you're familiar with, you know, the ball rolls and, let's say, due to friction, comes to rest at the bottom of a hill, at the bottom of a valley. So you can think of these valleys. Okay, these valleys are called local minima. Okay, these valleys are called local minima. And we would ideally like to, you know, get our ball into this deepest local minimum. But essentially what goes on is if we threw the ball, it could end up at any one of these local minima, at the bottom of any one of these valleys. Okay? So our idea is to use the surface that is defined by the in-sample error and exactly play this game of throw a ball on this surface and see where it rolls to. When it stops rolling, you've come to the bottom of some valley. Okay? So our idea, so E in of W is the hilly surface. Okay, and so we're going to throw a ball. Okay, throw a ball and see where it lands. It ends up. Okay. Now, in this general hilly surface, when you throw the ball, it could end up, you know, at any one of these local minima. Okay, and the general task of finding the minimum of an arbitrary function, for example, E in of W, that general task, you know, falls under the realm of optimization, which is a huge area in mathematics. So we're obviously not going to solve the big problems in that area. Okay, so we're going to, you know, just do this simple thing of, you know, following a ball that we throw and see where it goes. Okay, so there are two obvious questions that you might ask yourself when you look at this general approach. Okay, question one. How, okay, when you have, you know, hilly terrains and gravity and so on and so forth, we're all familiar with how the ball rolls and comes to a stop. There's gravity and there's friction. Okay? So how, but in this abstract terrain where the hills are defined by my E in of W, how do we, you know, throw a ball, and how does it roll down? Okay, how do we throw the ball and how does it roll down? Okay, first question. Second question. Okay, we want to find the weights that minimize the in-sample error, but, you know, we could get unlucky and end up with weights that have a very high in-sample error. Okay, so how do we get to the global minimum, not the local minimum? Okay, so how do we get to the what's called the global minimum, not the local minimum? Okay, not just an arbitrary bottom of a valley. We want to get to the bottom of the deepest valley. How do we get to the bottom of the deepest valley? Okay. So, how we throw the ball down and how does it roll? Okay, it's going to turn out, it's not going to matter too much how we throw the ball, so where you start in this space, and how does it roll? That's what we call gradient descent, so that's what we will derive. Okay, but how do we get to the deepest valley? Well, that's a deep question, so let's answer it. So let's answer this question. How do we get to the deepest valley? Remember when I told you that was the ugly child, but that was the well-behaved child? So we're going to go with the ugly, well-behaved child instead of the nice, easy-looking in-sample error. That's an absolute terror. Okay. Well, we're going to reap the benefits. Because that hilly surface I showed you, well, yes, in general, when you go and try to do in-sample error minimization or minimization of any function, you could have that wiggly surface. And if you had maintained that nice simple error function that we developed first, you would indeed be in that kind of a quagmire. But this in-sample error defines a surface that does not have that wiggliness. Okay, this in-sample error surface looks like this. None of that wiggliness, no local minima, just a global minimum. So all we have to really do is simulate putting a ball somewhere, anywhere, and let it roll. Okay, that's all we have to do. And why is that? It's because it's a nice, well-behaved ensemble error. It's a well-behaved function. So it looks ugly, but it's well-behaved. Okay, and that's why we chose it. That's one of the reasons why it's so extremely convenient for us. So we don't have to, we just put the ball and let it roll, and we know that it's going to come to the minimum. Okay. Now, mathematically, this ensemble error is what's called convex, and that's what implies this property. Okay. So it implies that property. And anytime you have a convex error function, you will have this kind of a property, and you don't have to worry about other values. There's only one value, and you'll get there as long as you know how to roll downhill. Okay. So we're now going to develop the methodology that allows us to roll downhill. It's called gradient descent, and it's going to be helpful to have some slides, some pictures to go along with the derivation. So, okay, gradient descent, or how do you roll downhill? Gradient descent. Now, how to roll downhill. Okay, I mean, you thought you knew how to roll downhill. No, we're going to teach you how to really roll downhill. Okay, now, the picture sort of summarizes what's going on. Okay, and think of the coordinate axes W0, W1, and in general you'll have W2 up to WD. So we're showing 2. Okay, and at any point in this coordinate space, i.e. at any set of weights, you can compute the ensemble error, and that's the height of that surface, that nice colored surface. The colors correspond to height. Okay, and as you vary the coordinate point, as you vary your weight, you trace out this nice, smooth, convex surface with a single global minimum. And now what's the idea? So what's shown there is you're at a point in this coordinate space, you're on the surface, and you look around, okay, and you have lots of directions that are available to you, and you pick one, and you're going to move. Okay, then you're going to look around again, pick one, and move. Look around again and pick one, and move. And that's the basis of this iterative algorithm. Okay, so at iteration t, you're at weights W of t. Okay, and you look around and pick a direction. I'm going to underline direction, v hat. And I'm calling it v hat because it's a direction. So it only has direction. It doesn't have, length. Only the direction is relevant. And so this is a unit vector that corresponds to direction. Okay, so you find a direction and then take a small step in that direction. Take a small step in direction v hat. Okay, so what is a small step? Well, we're going to define a step size. Let's call it eta. So eta is the step size. And let's be cautious, so we're going to pick eta small, so that we look around, figure out a direction to move, take a small step, and a small step, small step, small step. And hopefully in this way, by taking lots of small steps, we ultimately end up at the minimum of the ensemble error. Okay? And so the idea here is that we update to W of t plus 1, from W of t by adding a move of size eta in the direction v hat. Okay? Relatively simple update algorithm. Okay. The problem is, of course, we need to figure out what's v hat. And also, at the end of the day, we have to figure out what the step size is. Okay, but for the moment, it's a cautious, very small step size. So let's go back to what we're trying to do. We're trying to minimize the ensemble error. So we should take a step that decreases the error the most. Biggest bang for the buck. So basically, we're trying to ask, what's the direction in which we can roll downhill, and that's steepest? Okay. So decrease E in the most. That's the idea. Okay. So let's look at what E in is doing. So before the move, you have E in at W of t. And after the move, you have E in of W of t plus 1, okay, which is E in of W of t plus eta v hat, which, okay, because now we have chosen eta small, we can apply the first order Taylor approximation from calculus. This is approximately E in of W of t, the place you started at, plus the move dotted into the gradient, plus the gradient of E in at W of t dotted into eta v hat. Okay, So that's the first order Taylor approximation. If you compare where you were with where you are now, okay, the change in the ensemble error is exactly this term. So the change in En is approximately eta times the gradient of En of W of t dotted into V hat. Okay, this is the dot product of two vectors. The Cauchy-Schwarz inequality says this is always larger than the negative of the product of the norms. Okay, so this is always at least minus eta, the norm of the gradient En of W of t times the norm of V hat. Okay, the minus. So the minus corresponds to the picture. You know, you have the gradient of En, okay, is some vector, and you're taking the dot product with some other vector. We get to choose this direction, so we should choose this direction to be in the opposite direction, okay, but it must be a unit vector. And then we will accomplish this. We will saturate this inequality. Okay, so the biggest bang for the buck comes from choosing V hat in the negative direction of En. So V hat should be in the negative direction of the gradient of En of W of t. Okay, that comes from this analysis where the goal is to minimize, is to decrease the ensemble error the most. Okay, but this is not generally a unit vector, so to make it a unit vector, we should divide by the norm of the gradient. Okay, and so now we have the direction to move. We have picked a fixed small size, so we move in that direction, and now we reevaluate. Maybe the gradient of the surface has changed, so we pick the new gradient, move, 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 and so on. Okay, so this is illustrated. Okay, so we have a bunch of directions to choose from. We pick one of them, and then we move, 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 move. So we can iterate this process, move, 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 and so on. Okay. Let's summarize that in an algorithm. Okay. So imagine that you initialize your weights at iteration t equals 0 to W of 0. Now at iteration t, okay, let's suppose you are at W of t. So you compute the gradient En of W of t, and update W of t plus 1, equal to W of t plus eta times the gradient of En of W of t. Oh, sorry, minus, because the move is in the negative gradient direction, divided by the norm of the gradient. Okay? And you can update t to t plus 1 and repeat. Okay. And so this implements that idea of finding the steepest direction in which to move a little bit. Find the now new steepest direction, move a little bit, and so on and so forth. Okay. This algorithm is called normalized gradient descent. So we're going to call this normalized gradient descent. Normalized because you take the gradient and normalize it. And you always move in the negative direction of the gradient. And it's interesting. So an interesting piece of information. For any ensemble error, okay, if you take the negative of the gradient, that is a direction in which that error has to decrease, okay, for some small enough step size. Okay, so we're almost done, except what about the step size? How should we choose the step size? Well, I said you should be cautious and choose a small step size. Okay? But at the end of the day, we've assumed that the step size is fixed. So let me show you what can go wrong. So what is the right step size? Okay, and it's illustrated in the pictures on the right, but I'll draw them over here just as I explained it. Okay, so imagine that here are your weights, okay, and you have a very steep En surface. Okay, and you're at this point. Okay, so you're at this set of weights, and now you take a fixed step size, and that step size happens to be taking you here. So it takes you here. Well, when you make that move, you will find that, the ensemble error suddenly went from where it was to something too big, something much bigger. And then you say, but did you say that the negative of the gradient, so the gradient in this case is in that direction, because that's the downhill direction, so you'll move that way. It's just that, yes, the gradient does give you the direction in which you will decrease the most. Okay, it's the steepest. It's the direction of steepest descent, but it's just that your step size was too big, so that Taylor approximation was not valid anymore. So here the step size, so if this is a step size of size eta is too big. Okay. So you say, well, yes, okay, so in that case we should choose eta so small, so tiny that we'll never run into this problem. Or at least when it starts bouncing around like this, so when you get here it'll bounce the other way and then bounce the other way and so on and so forth. So when it starts bouncing around, you're already very close to the minimum, and that eta kind of decides the tolerance with which you will get to the minimum. Okay, so choose a very tiny eta. Okay, that seems to solve this problem. Except, okay, here's what could happen. So it's not quite as steep anymore, but let's say it's something like this. And you're not that close to the minimum, so you're somewhere here. And you knew about this problem, so you chose a very small eta. And then that moved you here, and you chose another very small eta, and another small eta, and another small eta. And you're continuing to make these small moves, move. By this time, you've got married, you've had kids, you've had grandkids. I mean, who cares about minimizing the ensemble error anymore? Okay. So the problem that can arise is if you're very far from the minimum, and you have chosen a very small step size to guard against this, it'll take you forever to get to the bottom. Okay. So ideally what we would like is some kind of Goldilocks step size, okay, where I think about, you're far away. Okay. Ideally we would like to take a big step, okay, and we're still far away, so we take another big step. Okay, and now we've gotten close, so let's take a small step, and then a small step, and so on. But this is not a fixed step size. So here, eta is too small. Here, eta is variable. Okay. So, if we're going to allow for a variable eta, then we somehow need to be able to decide, how far are we from the minimum? Because when we're far away, we want to have a big step size, and when we're close, we want to have a small step size. Okay? We would like this, but we need to know how far we are from the minimum. In general, that's not so easy to do. Okay? But let's try. Variable step size. Variable step size. Okay. Far from minimum, you want eta large. Close to minimum, you want eta small. Okay. Now here's one thing we know from calculus. When you're close to the minimum, and certainly when you're at the minimum, when you're close to the minimum, the gradient of the ensemble error will be approximately 0. When you're far from the minimum, okay, it's not necessarily the case, but usually the gradient is large. Usually the gradient of E in is much larger than 0, usually. Okay. So this suggests that the norm of the gradient is an indicator of how far you are from the minimum. So, conclusion, choose eta proportional to the size of the gradient. But if eta is proportional to the size of the gradient, and then the direction has the size of the gradient in the denominator, when I multiply these two, the gradient will disappear. Okay? And that leads us to regular gradient descent. Regular gradient descent just says, remove the norm of the gradient from in here. Now remember, the norm got in here because we were picking a direction and moving a fixed step. When we remove this gradient, basically what that corresponds to is pick a direction and then move a step whose size is variable proportional to the norm of the gradient. And this algorithm is called regular gradient descent with what's called a learning rate eta. So this guy here is called the learning rate. Okay, and it's summarized in the slide, but you've got the whole idea right here. Now I want to emphasize. Okay. So, star. Okay. So this algorithm, this gradient descent, you can use it to go to the minimum of any convex function, and you can use it to go to the local minimum of any function, providing that the function is differentiable, and you can get a gradient. So gradient descent works for any differentiable E in of W. And our E in of W was a very specific ensemble error. E in of W was equal to, and it's up there, I'll repeat it here, sum n equals 1 to big N, log of 1 plus e to the minus yn w transpose xn. Okay, this is our ensemble error, but you can use it to go to the minimum of any ensemble error. Now, okay, let's look at the cost, the computational cost, because now I want to introduce you to a sort of twist on this algorithm. And the main reason for introducing this twist is efficiency. Okay. So you can use this to minimize any ensemble error, but it can be inefficient. Okay. And here's the reason. Okay. Let's look at one step. So what happens in one step? In one iteration. Okay, in one iteration, here are the things that you do. You first compute the gradient, and then you update the weights. Okay, now here you have to update d plus 1 weights. So this is an order of d plus 1 operation. But let's look at computing the gradient. Computing the gradient requires you to compute the gradient of this humongous sum. Okay. So you compute the gradient of this humongous sum, which means you have to compute the sum of the gradients of these guys. Okay, which means that you have to compute, and this is an order of d operation, okay, and you have to do it n times. So this is order of n times d. That's costly. If your dimension is 1,000 or 1,000,000 and you have 100,000 data points, that's costly. And you do all this computation for what? For one small move. Okay? So, it's true. Eventually it'll get you to the bottom of this ensemble error, but when? Okay? And so in walks stochastic gradient descent. Okay, so in walks stochastic gradient descent, okay, which is what I'm going to tell you about next. Stochastic gradient descent, or how to roll downhill efficiently. Now, gradient descent is guaranteeing you that you will always minimize the ensemble error. Stochastic gradient descent does not guarantee you that. The basic idea is very similar to the perceptron learning algorithm, PLA. Okay, so it says, the ensemble error, En of W, is a sum, is 1 over n, and you can think of this term, so sum from n equals 1 to big N, of a little error for the data point xn. So it's an error between, W, it's an error between W transpose xn and yn. Okay, it's an error that's computed. It's an error term that depends on W, xn, and yn. And when you compute the gradient, you compute essentially the gradient for all these little error terms. So stochastic gradient descent, or SGD, basically says, don't compute all the individual gradients and then add them up and make one move. Pick a data point. Pick a random data point. Okay, so for this random data point xn, the error that you're currently making is E of W transpose xn, yn. So that's the error that you're currently making. Well, minimize that error a little bit. So in other words, make your move in your weights so that you at least make this data point a little bit better. Okay, so make E of W transpose xn, yn a little better. So what that means is that W of t plus 1 is going to equal W of t minus, your learning rate times the gradient of the little e, not the big E in, E of W transpose xn and yn. Okay? So that's the update. Now, it's kind of crucial that you picked a random data point, because what does that mean? That means that on average, the expected value of this update is exactly this. Is exactly the update. So the expected value of this, is exactly the gradient of E in. Because You picked a data point randomly. So the expected value is each of the possible values weighted by the probability, which is 1 over n. So you get the sum of 1 over n of these gradients, which is exactly the gradient of E in. Okay, so on average, the gradient that you're using is the gradient that you want to use. Okay, but it's not. But you're picking one term, one data point, and minimizing on it a little. Then you pick another random data point and minimize on it a little, and continue. Okay. So what is this guy? E of W transpose Xn and Yn is exactly the log of 1 plus e to the minus Yn W transpose Xn. Okay, so the gradient of this with respect to W, the gradient of E of W transpose Xn and Yn is exactly minus Yn Xn divided by 1 plus e to the minus Yn W transpose Xn. So you can compute this gradient yourself. Okay, it's basically, this is a linear function of W, so you pull down the coefficient, okay, and then you take the log, the derivative of the log becomes, 1 over that. Okay. And then you have to multiply here by e to the minus Yn W transpose Xn. So the derivative of this guy is this times that, okay, and then 1 times 1 over this guy, so that's the chain rule. But this is exactly equal to minus Yn Xn over 1 plus e to the Yn W transpose Xn. Okay, and so we get for this update W t plus 1 equals W of t, okay, minus eta times this guy. But the minus times the minus becomes a plus, so we get plus eta times this guy, which is plus Yn Xn, okay, times eta over 1 plus e to the Yn W transpose Xn. So this is the update for stochastic gradient descent. So you pick a random data point, make this update. Pick another random data point, make this update. But here, if I hide that term, you've got W of t plus Yn Xn. That's exactly the PLA update. Okay. Except the only difference is that you have this weighting term. Okay. And the other difference is in the PLA, Xn was a misclassified point. Here, it's a random point. So you will try to improve the situation for any random point. And so, this is the algorithm that people typically use instead of gradient descent just because of efficiency. We would like to use gradient descent, but it's a very costly algorithm. So stochastic gradient descent minimizes the error on, random data points one at a time. Okay. And so it's interesting to just see the performance for that error function that I showed you, the performance of, gradient descent on the left and stochastic gradient descent on the right. And if you look at gradient descent, it very smoothly arrives at the minimum. Stochastic gradient descent is bouncing around. It's bouncing around, and eventually makes it down. So it looks like, well, why? Okay, that doesn't look good. Okay, it's bouncing around. So on average, it's making sort of the same progress, but it's bouncing around because, at each step, you're not minimizing the in-sample error, you're minimizing the error on a particular data point, and that's why you bounce around. Usually the price for gradient descent is you have to choose a slightly smaller learning rate. You have to choose a slightly smaller learning rate. But this bouncing around looks less efficient. In fact, it's much more efficient because each of those steps in the stochastic gradient descent is one gradient computation. Whereas for the gradient descent, it's n gradient computation. So it's a much slower step, although it looks much nicer. Okay, so that's gradient descent. We've talked about logistic regression. Okay, logistic regression means, predict the probability. Okay, we derive the cross-entropy error function, which is an ugly-looking but very well-behaved error function. It has probability built in, and it's convex. You can optimize with gradient descent. Okay, or if you want to be bold and adventurous and more efficient, stochastic gradient descent. Okay. So, summary of linear models. Classification, we have the perceptron and PLA/pocket. Regression, we have, the W transpose X, the standard linear model, and the pseudo-inverse one-step algorithm that can minimize the in-sample error. And for logistic regression, we have, the sigmoid on the linear signal, And the algorithm for minimizing the ensemble error is gradient descent or stochastic gradient descent. That's a whole new algorithm for you. You can use it to minimize anything you want. Okay. We used it to minimize the ensemble error for logistic regression, getting you to the optimal weights. See you next time.